Welcome back. Please join me in welcoming Joachim Breitner to the stage. He is here today to discuss Winter, a Haskell port of reference implementation of WebAssembly. Welcome, Joachim.
Oh, thank you for the introduction. And welcome to my talk about how Winter is coming even faster now, very timely for the season. So before I start, I want to give you an outlook about what kind of talk this is. So this is a talk about how to make Haskell programs faster, but it's anecdotal, not educational. So instead of having some toy program that I've prepared precisely for the kind of comprehensive overview of all the different techniques you could use, this is really a tale of what I did in practice, which means you don't get all of the dramatic twists at the end, but rather the low-hanging fruit at the beginning. And the selection of techniques is not necessarily comprehensive, but rather just what I happen to be applying at this point. Also, it's not a tutorial, so some of these techniques, I'll give you a glimpse of it. You might want to look deeper in case you want to apply them yourself. So that said, let's get started. So where was I roughly a year ago working with Winter? So maybe first, let me introduce Winter. Winter is a WebAssembly interpreter, and I think that kind of explains the name. So WebAssembly, in case you don't know, is a low-level machine-like language that was designed to be portable and sandbox. So it runs in browsers most commonly, and it allows you to write programs that run in your customer's browsers at near native speed while not having to deal with JavaScript, essentially. But it's also useful outside the context of browsers. So some of the blockchain companies are discovering it now, and that's kind of the context where I was playing around with it. So WebAssembly is a language with a proper formal specification, which is pretty good. It's something that we as Haskells could maybe learn something from, but that's a different story. And as part of that specification, they have a reference implementation written in OCaml. The point of the reference implementation is not to be the thing you use to actually run it, but rather a tool to describe very precisely what a WebAssembly program should do. And then in practice, you would use production implementations like just-in-time compilers, WAS-in-time and V8 and others. So a reference implementation is not written with performance in mind. It's just not the goal. It's just not the need for it. So Winter is a part of that reference implementation, pretty much straightforward from looking at the OCaml code and writing Haskell code, done by John Mickey. And again, I want to stress that when John was writing this, he was not aiming for high performance. And that I want to stress that because it's an excuse for some of the choices that are being made. And I also really don't want to make this look like I'm talking badly about the kind of work he did. Well, but it turned out that I wanted to use this interpreter not at production level speed, but still fast enough to run certain interesting small programs. So I wrote a small test program. This is written in C. It just counts down from a computer scientist's million to 0, and does nothing else. And I can compile this using CLang to a WebAssembly program, and then run it using this WAS and invoke program that is part of the Winter Haskell program. So this is the program that's written in Haskell. And I can pass the RTS flag to it, which gives me a way of telling the runtime that's in the Haskell program to do certain things, in this case, to print timing statistics at the end. And running this program would actually take, well, 44 minutes, and it would require 6.3 gigabytes of memory. That's a lot, and quite absurd for the program that we're running here. So in order to use it for what I wanted to do it for, I had to sit down and make it at least reasonably fast. So here's an outlook of what we will achieve here in the talk. So these are commits that I did back then, and then we have graphs for the runtime and the memory usage. And we'll see that we can drop the runtime a little bit, then we look at the space leak and fix that, and then we do some more improvements to the runtime. Note, this graph is log scale. Some of these improvements are just so enormous that they wouldn't make the graph look any useful if it were in log scale. All right, so let's dive right in. We have 7 steps to look at. So the first one was, it's an interpreter for language that is imperative and has a virtual machine that has a linear memory. So just a bunch of bytes you can read and write to imperatively. And obviously that's a very common operation in such a machine. So I wanted to check how does the Haskell interpreter represent this memory? And it was easy to find the data type where this is defined. So we have a memory instance, and a memory is a an immutable vector, so the vector data type is by default immutable, that's put in a mutable box. So this mutable M is a bit more generic, but you could think of it as an IO ref, something you can just store a new value in. And immediately it's clear that this can't be fast, because just from looking at the type without looking at the code, I can tell that every time the program writes a byte to memory, the interpreter has to take the whole memory of the WebAssembly program and copy it with just one byte modified, and then put the whole copied vector, the reference to that vector, back in this mutable cell. And clearly, that can't be fast. So this, since we're already dealing with mutation here, and we are in a IO-like monad, so this M is a monad, typically IO or ST or something like that. So we already are in like an imperative programming style. So an easy choice, easy fix here was to use a mutable vector, which is also provided by the vector library, and it allows you to modify cells in the vector in place. We still have to put the whole vector, as we see here, inside one of these mutable boxes, because WebAssembly can grow its memory, and mutable vectors, they can mutate the elements, but they can't change their size. So whenever the WebAssembly program would allocate more pages of virtual memory, the interpreter would still have to copy the whole memory into a new vector that's larger, but that's an infrequent operation. And really, modifying bytes is the thing. And indeed, that was already a huge impact. We went down from 44 minutes to 30 seconds, and memory consumption went down a little bit as well. So that's great. What else can we do? Well, we've just seen that the code seems to be rather polymorphic. So we have this M type variable to stand in for an arbitrary monad, or typically a monad that has certain properties, like has these mutable cells. And the whole evaluator, the whole core part of the interpreter, was written in this polymorphic style. And this is great because it means I can now use this WebAssembly library and use it as in the IO monad or in the ST monad if I want to wrap some pure computation, or even some other monad that is like maybe a monad stack on top of IO or ST. But this flexibility comes at a price. With this code, the monad is unknown to the compiler. Only when I use this code from another module, another library, I specify which monad, in particular which monad bind operation to use. That means every time this function here, in particular the inner loop of the interpreter, needs to do one monadic bind or one do notation step, it has to put the continuation into a closure and then call this unknown function with the continuation, and then the monadic bind does the thing and returns back. So that's slow and expensive. How do I fix that? Now, I could just say, you know what, I don't really need this flexibility. I'm just doing everything on IO anyway. And it might have been true for the was and invoke function that I was using. But there must have been a reason why John wanted it to be flexible. So, and I also didn't want to go through the whole code and change every type signature everywhere. So instead, what we can do is we can use a specialized pragma. So this is a pragma that we just put next to the code. And we give a new type signature for eval that is a specialization of the eval's type signature. So note we have the same arguments. It's just that all the type variables are being replaced with concrete types. And these are precisely the types that I'm using this method at from some other module. And what the compiler will do is it will compile eval twice. Once the existing generic version, and then again the version with the monad being IO. And there it can do all kinds of optimizations. It knows precisely what bind is, and can put the bind code in there directly, inline it, can optimize it. And then when you use this code, this module from some program or some other library, and you happen to be calling eval at this type signature, then the compiler will recognize that there's a faster variant that it can use, and will use that. And that's when we get the benefit. So now we're down to 17 seconds, almost half, which is a nice improvement. Without changing this code, just adding more of these specialized pragmas. So now runtime is kind of reasonable. You can play around with that without getting annoyed. But the memory consumption of many gigabytes of memory for this small program, which doesn't even allocate any significant amount of memory, is still absurd. So clearly we have a space leak. And I didn't really know where to look. So what I did was to use heap profiling to get some idea. So I had to recompile the program using the flag enable profiling. And then I could pass the HY flag to the runtime of the running program. And this produces an output file that we can transform into a graph, and it'll tell us which types are filling up the Haskell program's memory. And the graph is very unambiguous. It's saying, well, it's all lists, and basically it's just linearly filling up the memory. So clearly we have a space leak. So I looked at where are we using lists in like the hot path of the program. I knew this is the interpreter, so the step and eval functions are the interesting ones. And I found quite a few uses of lists. In particular, I found quite a few uses of the list concatenation operator. And that is always a dangerous beast, because the list concatenation always has to copy everything on the left. So if you copy two lists, concatenate two lists, it'll create a new list that is a copy of the first list and then it continues with the second list. So the second list can be large, that's fine. The first one gets copied, which is dangerous if you keep appending something to existing list, because then you're copying the first bit and you're copying the next appended list and you're copying the next one and next one, and that gives you a quadratic cost of appending lists. So maybe something like this is happening here. Luckily, there's a very nice trick you can just apply to existing code without pulling in libraries. You don't need to get libraries for that. You can apply it very locally, and it's really worth knowing. And that is using difference lists. And it's very repetitive. So you have certain lists that you're just building up without using them another way until you're done. Then you can turn these lists into difference lists. So every time you see a list type, you replace it with the this function type from list to list. As it's a list where you don't know yet how it continues. The empty list you replace with the identity function. The singleton list you replace with the function that prepends one element to your list. The concatenation of two lists, and that's an interesting one, you replace with function composition. And here, this is where the magic happens, because function composition is O of 1, it's constant time. So it doesn't matter which way you compose these functions. And then at the very end, when you have accumulated a list and you want to use it maybe with some consumer of lists, you just take this difference list, which after all is a function, pass the empty list to it, and you're back in the world of normal lists. So that's a nice recipe. I find myself applying that over and over in different projects. And if you do it locally, you really don't need to worry about libraries for that or anything. So I applied that to one smelly looking piece in the interpreter, and suddenly we're at 61 megabytes. So clearly there was a huge space leak, and that fixed it. Also, the program was much faster now, which is not unexpected, because if you have lots of garbage in your heap that's still kept alive somehow, and the garbage collector has to do much more work. I looked for more use of the list operator there, and I found some, and at the end, we were down at 2 megabytes. So here we were still having a space leak. It would still grow, just much less aggressively than before. After more application of this pattern, we were down to 2 megabytes, basically constant. That's just the space that Haskell needs to run, and a much nicer runtime. That said, I'm not actually entirely sure why that fixed the problem, because difference lists are not inherently more space efficient or known to plug space leaks. The space leak is, just because you're not aware of it, is, well, Haskell is lazy. So whenever you have a computation with some input, it'll only do the computation once you actually need the output. But what if the input is very large and the output is very small? Input might be a large list and the output is a single number. Well, Haskell doesn't know that ahead of time, so it'll keep the input around until you need the output. But that's much larger memory, so that's bad. So often, sometimes it's good to be more strict, to be more eager, to evaluate this computation before you actually need it, so that the input is used, you have the small output, and the input, if it's not used anywhere else, can be freed and can be thrown out of your memory. And somehow in this operation, I might have made something more eager, more strict, and somehow plugged the space leak. I didn't further investigate. I was happy with that improvement. So on to the next. So this is a fun one. And it's kind of nice to see it happening, because it may be unexpected. So the main function of the interpreter, the eval module, the main module, was written like this. So you have a module name, and then you just define your stuff. And the effect is that all functions, all top-level functions in that module are exported. I changed that to just list those functions that are actually interesting to other modules that are actually used outside this module. And suddenly, the program was faster by 11%. So now the most low-hanging fruit is gone. We're writing now the improvements in percentages because the absolute numbers are less interesting. But still 11% is not to be frowned upon. So why does it happen? Well, if the compiler, in the second variant, or maybe let's look at the first variant first. If you have some top-level function like eval or step, and it's exported, the compiler doesn't know who will call it. Especially it doesn't know how often it will be called, what kind of arguments will be called. But if it's not exported, it knows that it sees every single possible call of that function. And that allows it to make optimizations based on that information. If it's only called once, it can inline it and then do more optimizations. Maybe all the calls pass a certain amount of arguments, then call array can do its magic, or the demand analyzer can do more. So by telling the compiler more about how your module can be used, the compiler can do more to your program. And it's also generally good practice for your fellow programmers and maybe yourself later to understand how this module actually works and what if it is relevant to the outside and whatnot. So it's always recommendable to do that. Okay, the next one is quite technical. I might lose some of you during this step. In this case, just wait for step 6 to come up again. But I found it very interesting. I learned myself a bit from digging deeper here. So I didn't really have a clear idea what to look next for. So I did something that's slightly advanced, but still useful. So you can ask the compiler, okay, after you did all your magic optimizations that Simon Peyton-Jones worked on for decades, what does the program look like then? And if with some experience, you can look at this program after optimization and look for good or bad patterns or things that or missed opportunities. And one way of doing that is to pass these flags to GHC. So let's do that here for a moment. The easiest way to pass flags when you want to target a single module and you're using Cabal is just to put them in the file as a pragma. And then I can build this. And now the compiler will spit out the optimized code in a little while. It'll spit it out in a language called core. It is a functional language, so it has lambdas and data types and things and case expressions, but it's much simplified from Haskell in one way, so much less syntactic sugar. But it's also more complicated because it's the types all around. It has lots of annotations. So basically, reading it, you have to learn what to ignore initially. And again, this would be a full tutorial to explain this. So just give a brief glimpse. So I was looking at the step function, which evaluates one instruction. And okay, it takes a code argument and some continuation argument. That's fine. And then it looks at the code to find out what is the next instruction. One common operation is the get local instruction of WebAssembly. And that's really important. So it's kind of hot path. And here notice something very fishy. The step function would return a function, which takes one of these config things and then do more work. Now, it's really great that Haskell allows you, well, maybe let's show, this is what you just saw in much simplified and slide and funny colors. So it's really great that Haskell allows you to use functions as first-class values and pass them around, and you can do great many abstract things with that. But it's not particularly fast. Because to create such a function value, you have to take all the free variables, put them in a data structure on the heap, so you have to allocate memory for that, you pass that out. When you want to call these things, you have to inspect it, how many arguments does it expect. You have to do a jump to an unknown location, which is always more expensive than just calling a function, a known function that is, compiler knows which function to call with the right number of arguments. So this is what we just saw, and as I mentioned, it's not necessarily fast. But where does this come from? This is not what the author wrote. So what the author wrote was something like this. The function takes the instruction, as before, but then returns, or I guess one will say, runs some computation in the ReaderT IO monad. Now, ReaderT is this monad transformer, and it allows you to take some monadic code that may be already using a monad like IO, and you just change the types, but not the terms anywhere, and suddenly you can pass a value, in this case config, to the very beginning, and you can use it wherever you need it without having to pass it around explicitly. But under the hood, ReaderT is nothing else than a function from config to IO result. So that explains why compiling this code will give you this code. But what we really would like to see here is this code. So notice that here the config parameter is just a parameter step. So step is now a function with 2 arguments. You pass it the 2 arguments, it does its stuff. There's no function values around, no calls to unknown function. Now, Haskell is supposedly this very smart compiler. So why doesn't GHG, why doesn't GHG turn the code that we saw into the code that we want when it's so much faster? Well, it's only faster in the common case, but not in the general case. It could be that let's look at this again. This is what we saw. It could be that some library is using the step function, passing one instruction, let's say addition, and then it takes the function that comes out of it and uses that function many times. In that case, the whole case EOF and maybe some more complicated things happening there wouldn't have to happen again. Whereas if the compiler would turn into this, then the case E only happens after you've passed this. So it would happen many times, and that would be a regression. So in this case, the compiler has to be conservative because he doesn't know what or doesn't see what we actually do here. So what do I do? Well, I didn't want to rewrite the whole code again and get rid of this ReaderT and just pass arguments around explicitly. That would be too invasive. But I found a pretty blunt trick of telling the compiler what to do. So I just put this noise in front of the case E, which is basically saying, okay, I'm going to unbox this ReaderT abstraction. And now I'm dealing with functions again. I write the lambda here to take the C, and then just pass it back into the ReaderT abstraction that the rest is. And the benefit of that is that this lambda now spans the whole body of the function. And that allows the compiler to turn this, after removing all the ReaderT new type things, into the code that we wanted to see. So how about, what did we get out of that? Still quite some nice 23% of runtime. So that's quite a lot. As a relief to all of you who are now thinking, oh my God, I'm using ReaderT everywhere, my code is just slow for no good reason, it may not be that bad. Because in this case, for example, after I've done all the other optimizations that we will still see, I could remove this hack and the code wouldn't change. Because at the end, the code was in a form that the compiler was good enough to optimize it. That said, be careful of big monad stacks, of polymorphic code in at least the inner loop of your very time critical code. All right. Step 6 is a rather generic one, maybe. So I looked at the code and I found that it was written in what's called continuation passing style. So we see that the step function, which takes one step of our interpreter, so it takes the code is basically the state of the machine, and it does one step, one instruction. But it didn't just return the new state, but rather it expects a function, here called k, which is typically the variable name for continuation, which would take the result of the step and then do more stuff. And we can see how this is being used in the eval function, which is nothing but a driver on step. It just keeps calling step until it's done. So if it's not done, we call step with the current state of the machine. And then we tell step to call eval when it's done. Now, there might be good reasons to use continuation passing style, in particular if you want to model like jumps or other control flow. But I wasn't quite sure if this was really needed here. Or if there was other reason. So I just started refactoring the code to be in direct style. So step would just return the code in the monad. And then the eval function would call step and then take the result and pass it to itself. So it's a very plain recursive function. And I could do this without breaking anything. And indeed, we have a nice improvement of the runtime here. This might have two reasons. One is, well, we're not using these functional values that I just mentioned are not always very fast. So the continuation itself would be just a closure where the code that's calling it doesn't quite know which function it is and so on. So we have none of that. And also, now the code is easy to understand for the compiler to optimize it. For example, the eval function could maybe be turned into a loop. in the machine code where you just do jumps rather than function calls. And that might improve the runtime a bit more. All right, almost there. On to the last one, the zipper. I really like this one because there are basically two tricks in one. So one is a domain-specific optimization, talking about how you create interpreters that are efficient. And the other one is a very generic optimization, which applies to any kind of data structure. And they're both the same. So let's talk about the interpreter view first. And we have to look a bit more at how Winter works. Again, this is a bit simplified, but the code that describes the current state of the machine, of the WebAssembly machine, has a stack of values and then a list of instructions to do on this stack. And then the instructions are things like push a value onto the stack, or addition, or subtraction, or return. But it could also be one of these labeled instructions, which are more like administrative instructions. So the idea is that when you're in a loop, you put one of these labeled instruction on the stack, and then you actually continuing inside the code that's an argument to this label to go inside the nesting of loops and ifs and maybe functions. So a concrete state of the machine somewhere in the middle of the relation might look like this: that we have the next instruction is one of these labels. That means we actually have to look inside, and there the next instruction is another label 2. So we have to look inside. And there now we have the addition of 3 and 2 in the stack machine. So the interpreter has to go through labeled 1, labeled 2, find the addition, which is now actually the instruction you can evaluate, pop 3 and 4 off the stack, push 7 onto the stack, the instruction is now gone. And that's in the new code state, but it has to still wrap that in the existing label 2 and label 1, which otherwise didn't change at all. Now that's kind of expensive. You have to go in this thing, into this code, find the position that you need to evaluate, do the change, and then go out again, putting them again around the new thing. So you're copying that again. And you have to do that on every step. So the solution from the point of view of implementing programming languages is to use a control step. So instead of having the code that we care about deeply nested, we want to have the code really as the top level data structure. So here's value instruction of the next thing we can evaluate. And then in the new field, basically on the side, we put the things that we don't care about. So this control data type has all the labeled data. So the state that we had previously before is now written like this, where we have the code, we have the labels and their suspended computation on the side in reverse order. So now what was innermost is now outermost. But most importantly, the 3 and 4 and the addition are now right away on the top level, the first parameters of the arguments of the top level constructor, which means that you can just do the computation without like constant time. You just don't have to go into something. So was this useful? Yeah, nice 36% of runtime. And actually, this kind of underestimates how important that was, because the program that we are running, the test program, wasn't very nested. There aren't many function calls, there are many loops, there are many ifs. But a real program has much more nesting depth, and the nesting depth, as it gets deeper, makes it ever slower. So that's why you can say that a small step interpreter without a control stack tends to be quadratic in runtime in the nesting depth. And this was very crucial to make this interpreter useful for more real examples. So I said, this is the interpreter point of view. There's also a generic point of view, and that is essentially what we did here is we applied what's called the zipper transformation to the existing data type of code. So what is the zipper? You usually get introduced to the zipper in the context of lists. So imagine you have a program that has a list, goes through a list, and maybe it has to find the position where it needs to do something, maybe change a value there, maybe look left and right, maybe move around, forward, back a little bit. If you're just doing this on lists, it means you have to find the spot, do the change, rebuild the list, find the spot, do the change, rebuild the list. And this rebuilding always is linear in the number of elements that you have before. So it's not efficient. The idea of the zipper is that as you go towards the position that you care about, you take these elements and you put them on the side, basically in reverse order. So once you're at the position that you care about, you have both the following elements as a normal list, but also the preceding elements as a reverse list. So you see the next element on top. And then you can do very efficient things like modify one value or move to the left or move to the right. So imagine you're implementing a Turing machine thingy like. Then that is a very general, a very nice way of modeling the tape. But this idea of the zipper is actually, doesn't just apply to lists, but you can apply it in a kind of mechanical way using derivatives or data types, fun stuff, to essentially every structured data type that you care about. And really what I did here was apply this transformation to the code data type. And that yielded the code that I had. And this also meant that I could do this rather complex transformation in a very systematic way, just by following the guidance that I have from knowing roughly what a zipper looks like. So at that point, I was happy with runtime. I didn't look for any further low-hanging fruit, and that means we're at the end of this little anecdote about how we made winter come faster. As a summary, maybe measure first to set up some example programs, get some good scripts going to get the numbers that you care about, maybe run a multiple times to reduce noise. It'll just be much more rewarding to do your modifications when you can then say, I will just improve the runtime by 50x or 30% or whatever. In general, use the right data types. Beware of lists. They're useful when it's the right thing to do, but they can be expensive when they're not the right thing to use. Simpler code is usually easier for you, for your readers, but also for the compiler to optimize. If you don't know where the hot path is, use the profiling. Hopefully the Haskell Foundation will make profiling much easier in the future, but it's dual already, so don't wait for that. You can get heap profiles, you can runtime profiles. It'll tell you what to look for. And at some point, you might want to take the step and look at the core and learn about unboxed data structures, about jump points, about all the things that you can see there to tell whether the compiler did to your code what you wanted it to do. And with that, I'm at the end of my talk, and I'm hope I didn't answer all the questions because I'm looking forward to a nice Q&A session now. Thank you.
Thank you, Joachim.